Vince Calhoun from the University of New Mexico and the Mind Research Network, who will talk about different dynamical methods and go maybe more into the details of how these methods can be applied on real and large data sets.
Okay. I have to say I really like the idea of a bowling party for a lab. That looks very fun. So it's great to be here. What I'm going to do is basically cover some more of the data-driven approaches. I don't know how to change this here. It's not the okay. Now? Thank you. Okay. And so I'll talk a little bit about those and some different metrics that have already been covered to a degree, and then I'll touch on some clinical applications just to give you a sense of how these things have been used in that context. So before I get started, I wanted to say that most of what we do is focused on the input to the approaches we use comes from group ICA, where you basically get sort of a fuzzy parcellation of the brain that's adaptive, right? And so you have these different components, spatial components, and then each one has a time course, and you can look at their relationship to one another, either statically or dynamically. And one of the reasons we like this is because it allows us to basically have a parcellation that's a little bit more robust to noise than a typical seed-based approach. We've been using this kind of an approach more recently, where we basically define component maps from say large normative data sets, Human Connectome Project or genomic superstruct data, for example, and then use these component maps as priors into a spatially constrained ICA. And if you do that kind of an approach, the advantage is you can apply it to new individual subjects. It's good for classification for some of the clinical applications, for example. And you can kind of see that here. It gives you nice sort of stable patterns. So this is two independent data sets using those input maps I showed you earlier, and you see the connectivity patterns are quite stable. They're sort of above 0.95 in terms of their stability. And then if you look at patient-controlled differences, in this case between schizophrenia and healthy controls, we also find very nice. Again, these are independent data sets. If we look at the most significant differences between schizophrenia and healthy controls, they're basically, again, above 0.95 or so correlated. So nice and stable, fairly robust. Before I jump in further, I wanted to kind of present a little bit of a spectrum, which has been touched on a little bit already, of more model-based versus more data-driven approaches. So on the sort of more model-based side would be things like dynamical systems models, which Michael will be talking about later. And so models on this end are basically specifying a lot more detail about what the underlying dynamics are. So you can then fit and test parameters according to that model. One of the challenges, of course, is that you can only fit the parameters that you've modeled, and you have to kind of know a little bit. You have to kind of decide what you think the system's capable of doing. You cannot fit what you haven't modeled in that sense. The good news is you can always extend the systems, to enhance flexibility, although you have to be careful of blowing up the number of parameters. On the more data-driven side, which would be sort of that clustering type approaches that were talked about, those are more agnostic to the underlying model. They're great when you don't have a real detailed sense of what the model should be, and you can constrain them based on how various modeling assumptions. You can kind of, again, push in either direction for either side. The issue is here is that data-driven approaches can be a little more black box in that you don't necessarily know, they're not analytically tractable, or you may not know whether the patterns are stable given certain combinations of algorithmic parameters. The good news, of course, is that you can check that quite easily in neighborhoods about a particular parameter. You can probe it with simulations. So again, the idea is not to say this or this is better, but that they're complementary to one another, really, and they're sort of informative. And it really is a spectrum. There's all sorts of in between. So the approach that we've been using is apply group ICA first, and then instead of taking a sort of static approach, we estimate these time-varying connectivity matrices, which have been talked about in a number of cases earlier. And then you take those time-varying matrices and you cluster those down into states or patterns of connectivity that individual subjects go into or out of or get close to or far from. And so then you can take that and you can further parameterize it by estimating individual states for given time points. So here, for example, this individual subject was in state 3, then 2, and then 4, using a Markov modeling approach here. And so this gives you the ability to then estimate various parameters and test for differences in those parameters. Here's an example from a schizophrenia data set where we have 5 different states estimated for healthy controls and schizophrenia patients. And so you can look at the patterns of connectivity and where those are different between the groups, right? So, and those tend to sort of group into a small subset of one or more states. So here, for example, we have a strong relationship between subcortical regions and sensory motor regions that are different in the patients versus the controls. But then you can also look at the parameters. For example, how much the mean dwell time in each state. On average, how long does an individual spend in a state once they enter it? And so if you test for differences in that, here are the 5 states. The healthy controls are showing significantly more dwell time in these more modularized states 1 and 2. The patients, they're spending more of their time over in these less modularized, weaker states 4 and 5. Okay? As Julia had mentioned, you can also allow these states to sort of be continuously overlapping with one another. So here's a way to visualize that. We have basically a state 1 versus state 2 grid. And you can imagine an individual moving at time point 1, they're moving around 2, 0, 1, 2, 3, et cetera, at different places on that grid. Okay? And here's another individual over here representing a completely different pattern in time. And so for any given point, we can parameterize that using a vector which we call a metastate. And so this is basically state 1, the position on the grid, and state 2, position on the grid. Okay? And then once we get these metastates, then we can calculate a lot of interesting metrics. For example, the number of distinct metastates they enter, how many times they fall in the same grid, the total distance they travel in that state space. And interestingly, when we looked at this at 4 of these in a schizophrenia versus healthy control comparison, we found that regardless of how we defined our states, so as Julia mentioned, you get very different patterns if you use PCA, ICA, temporal or spatial, k-means, hard k-means, fuzzy k-means, et cetera. But regardless of how we defined the states, we got the same basic pattern in terms of reduced number of metastates for the schizophrenia patients, for example, in all 4 cases here. And it's more of a global measure. It's kind of giving you an idea of how all these states are interacting, not specific to a given state. And you can calculate other interesting measures like hub states, which basically are metastates that are, once you enter them, you tend to spend more time there. So you can think of them as like sticky states. And so if you calculate hub states in this example data set, we find that schizophrenia patients exhibit significantly more hub states, more stickiness to their states. And their presence in those hub states is correlated to their negative symptoms. Again, giving us a little bit of intuition about what's going on here. So in terms of validation, there are a number of ways you can try to get at that, none of which is perfect, but which help us to kind of understand whether we can trust these things. And so you can do replicability is kind of the most basic thing we want to see. So here we have basically an analysis that was done on about 7,000 subjects split into 28 different groups of 250 subjects each. And we ran our pipeline on all of those independently of one another. And then we asked the question, do these state patterns replicate across those data sets? And they do. So we get basically about 0.7 or 0.8 in terms of their pattern similarity using a correlation. And their dwell time, or their percent occurrence time, was also consistent. So if there was a given state that people spent more time in, that was true across, tended to be true across all the different data sets. Likewise, we looked at whether these sort of clusters tended to have unique sort of peaks and had some evidence of being separable from one another. And if we look at more explicitly dynamic parameters, so the metastate metrics that we talked about, for example, we find that they also tend to be highly replicable across the different data sets. So these are those 4 different measures showing the distribution in those different data sets. And if we disrupt the phase, either using a consistent or inconsistent phase randomization approach, the distributions separate really completely from the actual value in the fMRI data. Suggesting the ordering is very important for these kinds of measures, as you would expect. Another way to try to validate this is to use multimodal information. Here we have a concurrent EEG fMRI data set. And from this, we can basically take measures of drowsiness. So we can use delta power, alpha power, theta power, et cetera. And we can order these fMRI states by that measure. So more drowsy, least drowsy over here. And you see more of these anti-correlations during the least drowsy, and it gets more sort of hyper-connected during the most drowsy conditions. So it's clear that sort of wakefulness is sort of a major factor in these states, but that's not the whole story. So here, if we look at sleep and wakefulness, this was an extended study where people did fall asleep and get into deeper sleep states from Enzo Tagliazucci's group. And we find that we get a very high ability to predict the sleep state. Here's the EEG hypnogram, which predicted sleep stage, and one of the DFNC state vectors. And they're highly correlated. So we can predict sleep stage, using these fMRI patterns. But if we focus only on the most wakeful condition, the most wakeful state, we also can do clustering within just those time points. And we find that we get predictable, using sort of cross-validated support vector machine prediction of those patterns, we find that we get predictable states within just the wakeful condition. Okay? So there does appear to be sort of a hierarchical information that's important to try to capture here. You can see here the predictability of the k-means measure was around 70-75%. Using a more adaptive windowing approach, dynamic correlation coefficient, that one did not perform very well. That was about 50 or 60%. We think because it's a little bit more susceptible to noise, but there are some things you can do to actually improve that as well. And I had mentioned sort of the wakefulness drives variability. Task drives variability too, a lot, right? So here's some data from Javier Gonzalez-Castillo's group, where they have blocked conditions of rest, memory, video, or math. And if you do a clustering on these dynamic connectivity matrices, you get task. It predicts task very, very well, over 90%. Not surprising, task impacts the covariation of the data. And here we have sort of how we modeled it was sort of an overlapping pattern of 4 different connectivity states corresponding to each of those tasks. But again, if you cluster in a higher dimensional level, or you cluster within task, you get these predictable patterns of correlation that shift even just within a consistent task condition. Another way to sort of see whether this is actually meaningful is, can it tell us something useful? And here, for example, we're looking at diagnosis. So we have bipolar, schizophrenia, healthy controls. And what we were doing here was comparing our ability to predict diagnosis using either a static analysis or a dynamic analysis or time-varying analysis. Sorry, I'm butchering your terminology a little bit here, but here we've got basically about a 60% ability from this static approach, which is pretty good compared to chance, which is 33%. But we jump up to about 85% if we use the dynamic information. So it's clearly improving our ability to predict diagnosis. And that's true in a number of different scenarios. Here's one more example looking at mild traumatic brain injury. So the REST fMRI data was able to predict better than diffusion information, fractional anisotropy here. But then if you look at static versus REST, we get from 78 to about 90% or so in that. And then specific networks that were most predictive tended to be both cerebellum as well as these sort of cortical sensory regions. Okay. Lucina Uden's group has been looking at sort of external measures of executive function and how those relate to these connectivity patterns. And so, here what she found, for example, is in 5 different states here, state 1 was highly correlated to a particular executive function task here, whereas state 3 was correlated to a different executive function task. And that was true whether, if you looked at sort of the first half of the data or the second half of the data. She got consistent patterns relating them. And then a couple slides just to touch on the null model question. Null models are very important to help us sort of evaluate and test specific questions about the data, about what's in the data, with the caveat that you should be very careful that your null model is kind of a narrow one, meaning if you're trying to test for dynamic or not dynamic, that's a pretty broad model, and I can break any null model with a specific simulation. Just like I can break any of my models with a specific simulation, given that. So it's not particularly useful to have a really broad question like that, given we don't know exactly how the brain is functioning, how these models work. In terms of measures to try to detect whether dynamics are there or not, again, that's a kind of a difficult question. One measure you can use was proposed was to look at kurtosis. Kurtosis is able to predict, it's very good at predicting large spikes in transition in the data. So a single spike, for example, drives the kurtosis way up. It's less sensitive to more subtle changes, for example, like this. Another measure, also imperfect, that we've looked at is something we call phi, which is sort of a time frequency-based measure. It's based on a wavelet coefficient decomposition. But if you look at a comparison of the two in this case, you see that the measure of phi is able to detect, it's higher in the case here where you have these three transitions, whereas it's low here where there's no evident transition. Whereas the kurtosis measure is showing you the opposite, right? So no measure is perfect, and I'm not trying to claim that one or the other of these is the best, but you need to be very careful and cautious as you try to apply these kinds of measures. Also keeping in mind that there is a spectra of dynamics. You can start from on this side where we have something that's statistically stationary and epicless. So we've kind of tried to force it to be to have the lack of epochs in the data, and we have something that can be stationary but can still exhibit a lot of transient dynamics. We have real fMRI data, and we have explicitly highly non-stationary data. So these are kind of on a spectrum. And if you use, an approach, you can, this multivariate phi measure kind of detects this spectrum. But again, we don't know what the ground truth is here, and so it's just sort of a caveat that you need to be careful in sort of thinking about whether the data is actually dynamic or not, transient or not, in what way. A few examples of some advanced metrics. Julia's covered some of these already. But instead of looking just at covariation over time, you can look at a combination of the amplitude of the correlation, the spectra, and the phase. So all three sources of information are used to separate states from one another. And so this we have shown, I think we show in this paper, it actually separates out some pretty interesting states which have similar amplitude patterns but very different spectra or very different phase patterns. In that case, it's the delay between the time courses. So that gives you an additional and sort of more advanced way. More information is being used to identify these states. You can go further than that and look for sort of transient patterns of spectral bands. And so even in the sluggish fMRI data that we typically use, we found evidence of at least 4 different sort of dynamic connectivity spectral bands. An ultra-low one, a sort of medium one, more of a broad band, kind of covers a lot of frequency, and then sort of one that's right in the bold range here. Each one of those has its own pattern of covariation. Think of it as a state of covariation. And then interestingly, you can look at these off-diagonal patterns, and they're not all flat. In that, for example, here you see a strong evidence of basically communication occurring between this frequency band and this frequency band here in this network, which is the default mode network. Okay. Similar to the CAPS approach Julia mentioned, you can go to basically avoid assuming that these transitions are smooth. In this case, a windowless approach where you might imagine that, say you had two different patterns of covariation occurring here. If you're using something that assumes that there's a smooth transition, you might get an artifactual intermediate state here, estimated, right? And so if you use a windowless approach on some ground truth simulated data, you get back a pretty good representation of the underlying ground truth for either approach if it's smooth. But if you randomly shuffle it, the windowless approach works well, and this one does not, because it's assuming some temporal ordering and smoothness in those transitions. I'm going to skip the next slide and just jump here. Again, talking about sort of first and second order time variation. You can imagine taking a single time course. In this case, what we did was we computed a windowed measure of the amplitude of low-frequency fluctuation. So we basically computed a spectra and then computed the ratio of high to low power as a function of time. So then we have a measure that sort of changes over time in a bunch of these time courses. And then we can cluster those into sort of states based on that sort of first order measure. We can also do our standard covariance-based measure, and then we can look at how they relate to one another. And indeed, there are cases where they're tightly coupled. There are cases where they're different from one another, giving you different information. And you can see cases where they both are associated with external measures. For example, here's a working memory measure that was correlated for the two. Similarly, extending a covariance-based measure to looking at also sort of a derivative-based measure. And I think this is a little bit related, not the same as what Julia mentioned, where we're kind of looking at whether information is flowing into or out of a given state over time. And so you can see in this kind of measure where this is their derivative, this is the covariance measure, you can see these three states over here are showing a lot of sort of traffic in and out of the state because of these high amplitude negative and positive values in the derivatives. And again, we shouldn't ignore, as Julia mentioned, the spatial dynamic information, not just the temporal dynamic information. One of the ways we've approached this is to use essentially ICA-based measures projected back into voxel space to get basically changes over time within different domains. So here's a default mode network, for example. Here's a subcortical network. And you can kind of expand this out to show basically the different spatially varying basis functions that we've identified using ICA. And then you can also parameterize this and test for group differences in these spatial boundaries or spatial parameters. If we do this in schizophrenia, for example, we see strong, significant differences in mean dwell time between, for example, these subcortical regions. Okay? And then the last sort of advanced measure, and I'm not going to go into details on this, but you can use more explicitly memory-based models, in this case a deep learning model using something called a recurrent neural network to model joint spatial and temporal dynamics. And so in that case, you would get your sort of output is spatially evolving patterns, and in the time domain, you can actually use this type of model to predict future time points. You can use it to predict task onset or other kinds of information. So now let me jump through just a few examples of clinical applications. I think I've got about 8 or so slides here, each on a different example. In this case here, we've used essentially a dynamic connectivity or time-varying connectivity approach to look at individuals along the mood psychosis dimension. So we have basically schizophrenia, schizoaffective disorder, bipolar disorder, and healthy controls. And each of those groups is actually quite separable into unique patterns of connectivity within the most dominant dynamic pattern that was estimated from the data. And here you can kind of see how those different groups sort of interact with one another more or less in different states. We can also go sort of back a step to individuals that are at clinical high risk for schizophrenia. I'm just going to focus you sort of over here. You know, for the 5 states, basically 3 of them were showing substantial group differences between the clinical high risk, early onset schizophrenia, and healthy controls. And if we look at the meta-state metrics that I had mentioned earlier, you see that this clinical high-risk group is showing an intermediate value between the schizophrenia group and the healthy control group along those measures. So they're kind of not, they're reduced compared to healthy controls, but not as much as are the schizophrenia patients. This is an example from ADHD, attention deficit hyperactivity disorder. And one of the points to make here is that if we look at this global measure, these global metastate measures, we find reduction in 2 of the 4 measures, in contrast to schizophrenia, which showed severe reduction in all 4. But if we instead of focusing metastate measures on the entire matrix, we focus on subdomains within that matrix. So say default mode networks connected to themselves. What are the metastate measures of those? And so here's an example. We have, I think, about 7 different sort of default mode networks in this domain. We actually get the opposite pattern in terms of the metastate measures, which is not necessarily surprising when you think about it, because we're looking at some different data at a different scale, right? But I think there's actually a lot of work that needs to be done to figure out what is the best scale to be looking at, given the question that you're asking. You know, voxel level, whole brain level, domain level, et cetera. Let me explain and talk about this a lot more in this paper. Age drives connectivity quite strongly. And so here we've got an analysis of individuals between age 2 to 20. And I'm showing you 2 states, state 1 here, state 6 here. And you look at the dwell time for state 1, and you see that it decreases as age goes up. Whereas this one, it strongly increases as age goes up, with a hint of nonlinearity there. And so basically individuals are sort of transitioning out of this more weakly connected state to this more strongly interconnected state as they're getting older. This is consistent with an analysis here at a much narrower age range between 6 and 10. This is from the Generation R data set. And we found for age basically a strong relationship of age going from this more weakly connected state to this more strongly connected state. So the younger folks were here, the older folks were here. And then if we look at autistic tendency parameter, the social responsiveness scale, we see that basically those individuals tended to be in this more weak state even at the older ages. So there was a little bit of a delay there. Although this particular analysis wasn't explicitly longitudinal, so it was cross-sectional. And if we look at the more severe autism, this is some of the ABIDE data. We find similar to schizophrenia for those different metastate measures a reduction, really. So they're less dynamic, less fluid, not as severe as in schizophrenia. And the degree of that really correlates with their autistic score, ADOS score. And so you can see that here in just the patient group. And then lastly, this is an analysis looking at Alzheimer's and mild cognitive impairment. And so in this particular case, we actually find that two disease groups, one that was sort of a vascular disorder, subcortical ischemic vascular disorder, and Alzheimer's disease, which has been hard to separate from one another, are actually quite separable using the transition time in which they move between this sort of weak state 2 and this strong state 3. Okay, so this kind of summarizes, I know that's been kind of a fire hose of results, so to speak, and it's why I've tried to cite papers below in case you want to go look at the results. But there really is a lot of evidence of these dynamic measures being useful in terms of separating and characterizing these patient groups. In particular, this one was quite interesting, this sort of range between clinical high risk, early onset, and chronic schizophrenia, for example. Just another example of where these dynamic measures can be useful is just to see what's going on in your data, for example. This is a measure of vascular reactivity basically it's a sort of a block design. You're getting CO2 inhalation, right? And if you analyze that data with a dynamic connectivity measure, you see here in this particular plot we have 5 different state occupancies represented as a function of time, and it's pretty clear just from looking at this state 2 is very different once that first CO2 onset occurs, right? And then it gets to be much more, it never fully recovers, right? And so this helps you to see, well, yes, I can estimate resting networks from this data, but anything after the first CO2 response is actually conditioned upon that CO2 input and is not the same. Okay. And then just a few slides. We try to make our software available to the community. And so this just gives an example of, at this website, you can download these toolboxes. To drill down a little bit more, within the GIFT toolbox, which implements ICA and spatial constrained ICA and a lot of different options, we have a dynamic FNC toolbox, which lets you produce, basically you can set parameters and you can produce plots like the ones I've shown in these figures, and test for these various parametric differences that I've been talking about. So it is available either in a MATLAB fully sort of open package, or we also have it compiled into a runtime environment in case you don't have MATLAB and want to use it. And we also have a NIPIPE interface to it in case you want to call it from a Python tool. Thanks to my lab and to the many collaborators that I've worked with, and all of you for being so patient during this talk. So with that, I'll conclude and see if there are, I think we've got time for a few questions maybe.
Yeah, sure.
Yeah, okay.